Here's the 2004 problem. Take a moment and read this. Look at the table. So what we're talking about here is not molarity, but absorbance, but it is a direct analog for molarity. If the molarity doubles, the absorbance will double, assuming you have a colored compound, obviously. If the absorbance reduces to 1/3, that's because the molarity went down by 1/3. It also has a constant here of absorbance. The amount of absorbance will depend on that individual chemical. And so for this chemical X, we have a constant right here, which I've rewritten as this. So calculate the initial concentration of the colored species. Well, initial, right? What's the concentration? Well, it's a direct analog of this. Well, we already know the absorbance, and we know essentially the conversion between the absorbance and molarity, don't we? Because this has molarity in it. If I could cancel out the centimeters and multiply by the right thing, you know, I could get the molarity. And here's my version of it, which I think is clearer than theirs. Frankly, I don't understand what this is, so I'm going to ignore it. But I noticed that when I do this, I get the correct same answer, and it makes a lot more sense to me. I took their absorbance, which is a unitless number, and multiplied it by the constant and by the distance that it went through. Notice, remember, it depends on how far, of course, that you shine the light through. If you shine it through more chemical, then it absorbs more, right? So how wide is the container, the cuvette of the solution? It matters. Well, it's 1 centimeter wide, which is fairly convenient for us. Just make sure that your units cancel. This centimeter cancels that centimeter, and I get molarity, and I did get the same answer as they did. So it's a first order reaction, so we know that this is the integrated rate law. You can find this back at the front of the booklet. And what do we want? The rate constant. Okay, well, you can pick any line, but it's easier if you pick line 1 and 2, because then time is 0, and then the time passage is done for you, because 35 minus 0 is 35. So the passage of time is 35 minutes. Remember, it's not the time on the line that's the value of t. It's the passage of time between the two things that you want to consider. So if you pick line 2 and 3, you have to get, what is that, 8.8 minutes? So here's the value of ln, here's the value of the absorbance at the time run. Here's the absorbance value at time 0. Here's the passage of time. This is a value, ln of this. This is a value, ln of this. Subtract them, divide by 35 minutes, and we get a value for K. Remember to put the unit, and it is not minute, it is per minute. K will always have its time on the bottom of the fraction. Also, I know a lot of times we deal with seconds, but doggone it, if you put seconds on this, I bet they give you 1 out of 2 or something for this. In fact, this B problem may only be 1 point, in which case you missed the whole thing if you put seconds, or if you put minutes on the top as a unit. This unit is on the bottom, under this number. Take a look at C. Calculate the number of minutes it takes for it to drop from this to that. Okay, so we know it was this and to this, and notice the time is unknown. So the passage of time is the question. Now we know K, right? We borrowed K and we put it here, and it goes from amount original, which would be this, to this amount. This is the amount at the time being considered, and we can do this value minus this value divided by this one, and the units will pop to the top as the unit, and we can solve for T. Calculate the half-life. Well, this is the easy one. This formula is at the front of the booklet. Just to go back and find it. If you've done it enough, you may even remember that ln of 2 is 0.693, and it doesn't matter. You can put it in the calculator and simply divide. This one involves the Arrhenius equation, and okay, this is for the super nerds only, so if you want to skip ahead, that's fine. Now, the Arrhenius equation is not actually in the test, but I think it's a little bit math interesting, so I'm going to put it in here anyway. So, label the vertical axes of the graph. Well, they told us this is a first order reaction, and boy, do they think that you know that if you got a negative slope straight line for a first order reaction, that means that the axes are ln of K and this is not true. This is time. Then if you had the Arrhenius equation, you notice that when it's, this is it, you're not going to memorize it obviously, it's an analog for a straight line, which means that this makes an analog for m, which is the slope. So this is essentially that, equals, and if I solve for activation energy, energy of activation, then I can solve for the energy of activation if I know the slope. If I knew the slope, and notice they don't ask for a value. But if I knew the slope, I could then multiply by negative r, which I would look up in the booklet, and I could solve for the activation energy.